At the beach or at the swimming pool, you'll notice that it's easier lifting things in water than out of water. Submerged objects experience buoyancy, an upward force that we call buoyant force. To understand buoyant force, consider this solid block beneath the surface of a body of water. We draw sample force vectors showing the forces that water exerts on the block. Although water pressure has no preferred direction, forces due to pressure act at right angles to the surface. Notice the vectors are greater against the bottom of the block. Why? Because water pressure is greater there. Why? Simply because the bottom of the block is deeper. Remember, water pressure depends on depth. We see the lengths of the vectors at the side of the block are progressively longer with greater depth. This makes sense. But notice another thing. The vectors at the sides of the block are equal and opposite in direction, so they cancel. That's why I'm canceling them. I'm doing something else. I'm representing the force along the top with a single vector, then along the bottom. This pair of vertical vectors is due to the difference in water pressure against the block's bottom and top surfaces. When I combine this pair of vertical vectors, the resultant is the net force on the block in red, which represents what we call the buoyant force on the block, abbreviated BF. For a block at rest, the only other force acting on it is its weight, mg, which I also draw in red. Center of mass is in the center. The overall net force on the block is BF minus mg, where BF acts upward and mg downward. If BF is smaller in magnitude than mg, that is, weight is greater than buoyant force, the block sinks. If BF is larger in magnitude than mg, the block will rise and float on the surface. In the case where BF equals mg, the block would neither sink nor float. Something that neither sinks nor floats is a fish. Is there a buoyant force on a fish? Most certainly, for its bottom surface is deeper in the water than its top surface. And how much buoyant force acts on it? That's right, just enough to balance its weight. So the BF on the fish equals mg in magnitude. So what's the net force in the fish? These equal and opposite forces cancel to zero. And the fish is happy because it's at one with its environment. Interesting? Which is to say, yum? I hope so. I've used the simple cases of a block and a fish beneath water. The same reasoning applies no matter what the shape of the object. Some part of anything submerged is always deeper than other parts, so there will always be unequal pressures, and the horizontal components cancel out. So if somebody asked you why a heavy boulder is easier to lift when submerged in water, could you offer an explanation? Would you begin with the fact that the water pressure increases with depth? That the bottom of the boulder is deeper, so there's more water pressure acting up against the bottom than the smaller water pressure pushing down on its top? And the difference in upward and downward pressures result in different size forces? The net force of which is the net upward buoyant force? Would your explanation be something like this? I hope so, for if so, you've got it. Let me leave you with a question. If liquid pressure were the same at all depths in water, would there be a buoyant force on a boulder beneath the surface of water? Why or why not? Until next time, good buoyancy.